Okay, so today we're going to be graphing rational functions. We're going to be dealing with the things like domain and range, vertical and horizontal asymptotes. We're going to be needing the y-intercept. We're going to be diving into something new like end behavior and asymptote behavior. And then we're going to sketch and graph as well. So let's get started. So right now we have the steps and musts when graphing rational functions. It's this entire list right there. We're going to need asymptotes, vertical asymptotes, and horizontal asymptotes, y-intercept, x-intercept, and zeros, holes, table of values, the sketch and graph, which will need to be labeled with proper scale, and then we're going to do end behavior and asymptote behavior, which is fairly new. And I'm going to do my best to explain them to you. So first things first, asymptotes. Rational functions also often have asymptotes. An asymptote is a dotted line in which the function gets closer and closer to but never touches or equals the asymptote. Never equals the asymptote. We have vertical asymptotes, that's this one right here. We have horizontal asymptotes, that one's right there. And oblique asymptotes, which are slanted, and you find that by using long division with the numerator and denominator and all that jazz. So first we have a cheat sheet. This is how you solve for the VA and the HA and the x-intercept and the y-intercept. So for the vertical asymptote, you solve for x with the denominator of the rational function. With horizontal asymptotes, there are three cases, meaning y equals 0, the leading coefficient of the numerator and the denominator would be the horizontal asymptote or the oblique asymptote as well. For x-intercept, we solve for x with the numerator. And for y-intercept, you substitute x equals 0 into the rational function. So vertical asymptote, it's the zeros of the denominator. Right there. Solve for x with the denominator, that's your VA, your vertical asymptote. And then we have horizontal asymptotes, and there are three cases. Case number 1, if the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote would be y equals 0. So that's case number 1, and that's numerator less than denominator. Case number 2, if the degree of the numerator equals the degree of the denominator, then the horizontal asymptote would be the leading coefficient of the numerator and the leading coefficient of the denominator. Y equals 3x plus 1 over 2x plus 1. The horizontal asymptote would be y equals 3 over 2. That would be your horizontal asymptote. So there, and that's the numerator. The degree of the numerator equals the degree of the denominator. That means they have the same exponent. So as you can see, both of them were x to the power of 1. And then we have case 3, if the degree of the numerator is greater than the degree of the denominator, then you're going to use long division with the numerator and the denominator to find the OA, the oblique asymptote, which means you don't have a horizontal asymptote, you have an oblique asymptote, and that's numerator greater than the denominator. And the degree is just to what exponent. I'll give you a moment to write that down. Okay, moving on. So end behavior. As x continues to negative infinity or to positive infinity, the graph approaches the HA, the horizontal asymptote. Where does the graph lead to? And indicate whether it approaches from above or below the HA by using the negative sign right here or the positive sign right here. The negative sign equals below and the positive sign is above. So it has to do with the horizontal asymptote. In some cases it is 0, but that's just for an example. And I'll show you with the rational functions. I'll show you what it means once we begin, and I'll show you where it leads to and how is it approaching. Where does it approach? Where does it lead to? Things like that. And then we have asymptote behavior, and that has to do with the vertical asymptote. The behavior of the graph around the vertical asymptote going in the direction of positive infinity or negative infinity. And indicate whether the section of the graph is before or after the VA, and you use this negative symbol or this positive symbol. So that's before, left of the VA, or right of the VA. And I'll show you what this means with the based function rational graph 1 over x. So we have the base function, the rational function 1 over x, and you see I have it graphed here as well. We can see the HA and the VA all labeled here, dotted lines. So the VA is x equals 0, and the HA is y equals 0, and there are no x-intercepts and no y-intercepts. We have the domain and range right here. We're going to be doing domain and range for every rational function that we do, and it's mostly not going to include the VA or the HA. As you can see here, we have our table of values of what it means. We have the table of values there. And then we have the end behavior and asymptote behavior. So listen very closely. As x proceeds to negative infinity, y approaches 0 from below. So as x approaches negative infinity here, y approaches 0 below the HA. So we use that negative symbol. So as x approaches negative infinity, we have our graph here that's approaching 0 from the negative side. Listen closely. As x approaches infinity, y approaches 0 from above the HA. So as y approaches infinity, we have our graph here, and it approaches 0 from above the HA. Positive symbol. So as x approaches infinity, y approaches 0 from above the HA, so we use the positive symbol. So that was end behavior. As it approaches infinity, it approaches 0 from the positive side. As negative infinity approaches 0 from the negative side, so it's 0 negative and 0 positive. So it's end behavior. And now we're on to asymptote behavior. As x approaches 0 from before the VA, y approaches negative infinity. So as x approaches 0 from before the VA, values less than the VA, y approaches negative infinity. So as we approach the VA, y continues to negative infinity. As we approach the VA, y proceeds to negative infinity. From values less than the VA, y approaches negative infinity. See, it's going down. It's going to negative infinity as it approaches the VA. For as x approaches 0, positive, so for values more than the VA, y approaches infinity. So as we approach the VA, y goes to positive infinity. For values more than the VA, a rational function, the y approaches infinity. The VA right here, y is going up, meaning y approaches infinity. So that's, I'll give you a minute to write down the end behavior and the asymptote behavior. And if you want to go back and listen to the explanations again, just so you can really understand end behavior and asymptote behavior, you go ahead. So the VA, remember, are the zeros. So solve for x with denominator. Remember our cheat sheet. 3 cases. So solve for x with numerator. So I'll give you a moment to write this down. There you go. So the numerator, the degree of the numerator is less than the degree of the denominator, which means it's case number 1, which means our HA is y equals 0. Our zeros for the numerator, there are none. We solved x with the numerator. There's no way to solve for x with the numerator, which means there are no x-intercepts. And our y-intercept is 3 when you plug in 0 into 3 over x plus 1, plug in 0, then our y value for the y-intercept is 3, so it's 0, 3. And we have enough information to graph this now. So there's our graph there. So as x approaches negative infinity, our y value approaches 0 from below the HA, which means we're going to use this negative symbol here. As x approaches negative infinity, our y approaches the VA of 0 from below. So it would be 0 minus. As x approaches infinity, our y value approaches the HA of 0 from above the HA. So we're going to do 0 positive. Asymptote behavior. So as x approaches the VA from values less of the VA, our y value continues to go into negative infinity. So as it approaches the VA, our y value approaches negative infinity. Okay, and for values after the VA, as it approaches the VA, our y value approaches infinity. So y would be approach infinity as for the behavior around the VA. And now we're going to do our domain and range. for our extra points, we're going to use -2 and 2. And there are extra points. Moving on. I'll give you a moment to write that down. Okay, let's begin. Okay, so we have our graph here. And now let's do end behavior. As x approaches -infinity, the graph approaches 2, but above the HA. So it would be y approaches 2 above the HA. As x approaches -infinity, the graph is approaching 2, so a graph approaches the HA, but below the HA, so we're going to use a negative symbol. So as the graph approaches -2, so the VA, before the VA, y approaches infinity. So as the graph approaches the VA from before, y approaches infinity. As the graph approaches the VA from after the values of the VA, y approaches negative infinity. And now we're on to the domain and range. And now our extra points. And there are extra points. So that's graph number 2. And ready. Okay. It's case 1, so our y would be y equals 0. The numerator is 5, so we have no x-intercepts. And then we have our graph there. As the graph approaches negative infinity, our graph here approaches the HA, but from below. So it's going to be 0 from below. As the graph approaches infinity, the graph approaches the HA, but from above. So it's going to be 0 plus. As the graph approaches the VA from the values below, y goes to negative infinity. As the graph approaches the VA from values more than the VA, our graph approaches infinity. Now for our extra points. And there are 2 extra points there as well. So that's all our graphs here today. I would like to thank you very much for watching. I hope you found this helpful in how to analyze rational graphs and how to graph them as well. Thank you very much and have a wonderful day.